this problem, we are going to set up an exponential growth equation for the situation presented and then answer some questions. So we've got a painting that has this value of almost $73 million in 2004. It was originally valued at $26,000 if we take 1950 to be the initial year. So they want us to find the growth rate accurate to 3 decimal places. And it's telling us to use the notation V of t. So we know V of t is equal to our initial value, and then we want to apply this growth rate naturally, so we'll use the base e raised to the kt. Now the goal here is to solve for k. We only have one equation, which means we should have enough information to evaluate all variables in this equation here other than k. So the output, V of t, is the value after, was it 54 years of growth? So that's the $72,846,000 goes in for V of t. Our initial value, V sub 0, is the 26 grand. E raised to the k, and then we know this was beginning in 1950, and the resulting value here is 54 years later in 2004. So the t value is 54. So we have to solve for k. So we're going to divide both sides by the 26,000 to get the exponential factor by itself. And then we will write this as a logarithm. Natural log of this ratio here over the 26,000 equals our exponent, which is 54k. And remember, if you divide both sides, on the right side of this equation here, you get k times 54 or 54k. Same difference. This was just that ratio there, so I'll write out all the steps here. So that's how we got that logarithm. Natural log because it's base e. Remember, the argument of our logarithm is the output here, and then the exponent is what the logarithm is equal to. So our k is going to be the natural log of that ratio there divided by the 54. So we'll put that in the calculator to figure out what that is. So we have the natural log of our 72846,000 divided by our 26,000. 1, 2, 3. Close parentheses, divided by 54. So here's our growth rate, and then we will just round that accurate to 3 decimal places is what the problem is asking for. So we'll use k is equal to 0.147. Now we have what we need to answer a question like B, which is asking us for the value of this painting, which was initially $26,000, growing at what we now know to be approximately 14.7% for, let's see, if the base year is 1950, this is 77 years later. So 77 years. And this will be the answer we need. So we'll take the 26,000, e to the 0.147 times 77. And they want us to round this number to the nearest million, which means our answer would be let's see, the million is 7 decimals or 7 place values from to the left from our ones place. So we'll do 1, 2, 3, 4, 5, 6, 7. So our 1 here is the millions. So if we round that, that becomes a 2, and Now we've got our 1, 2, 3, 4, 5, 6 zeros at the end. So looks like $2,142,000,000 would be the value rounded to the nearest million in year 2027. Now to estimate the rate of change, remember the whole point of this continuous growth model is that the rate of change is always 15.7% of whatever the value is in a particular year. So we just figured out the value in the year we care about. We know it's let's actually use the unrounded value. This value here was this is the value of the painting or art, the painting in 2027. So if I want the rate of change, I know the value now. It's just a matter of multiplying by 0.147, right? The growth rate. And then if we round this number to the nearest million, we're talking, let's see, 1, 2, 3, 4, 5, 6. So that 4 is the millions place, which becomes a 5. 1, 2, 3, 4, 5, 6. And this would be dollars per year would be the units tied to this rate of change. So roughly $315 million if we round that off. You could find the derivative instead of taking that approach. This would be the more straightforward approach, but finding the derivative, hopefully you'll see, is going to amount to the same thing. Remember, the derivative would just be a matter of rewriting your continuous growth model and then multiplying by the derivative of the exponent and then evaluating at the t value we care about. And if you see this, let's see. I need to extend the page. When I plug in 77, if this is the derivative, we got that value, right? That was the number I had in my calculator. So it is just a matter of multiplying by the 0.147. And that's how we got this number here, which again, we just rounded to the nearest millions as requested. So there's our answer for part C. And then the last question wants us to answer how long it's going to take this initial amount of 26,000 growing at 14.7% to reach 4 billion. So we got 9 zeros after this 4. So we would divide both sides. Let's get the ratio first. We'll divide both sides by 26,000. I can cancel out 3 zeros. I know that because there's 3 zeros in both of them. So we'll just leave it as 4 million over 26. Equals e to the 0.147t. We'll write it as a logarithm. So we got the natural log of that ratio there equals our exponent. And to solve for t, we're just dividing by 0.147. So let's see what that comes out to be. We got the natural log of our 4 million divided by 26. And then we'll close parentheses and divide by that 0.147. There's our t value, which if we round to the nearest year, will be 81 years. So it's going to take 81 years after 1950 to reach the $4 billion mark. Hopefully you find that helpful. Thanks. Bye-bye.